Hello and welcome back to Foundations of Deep Learning. In this week, we will discuss all about convolutional neural networks. And as you know, CNNs are at the core of the deep learning field today. We will first start this lecture with a brief overview of ConvNets and look at some of the current applications that have been revolutionized by them. Then we will touch a little bit on the history of how people came up with this idea of using convolutions. And this primarily comes from neuroscience observations. Next, we will look at convolutional operations in more detail, and we will look at the main advantages of convolutional operations. Then we will briefly look at some of the miscellaneous convolutions such as transpose convolutions, group convolutions, and so on. And then we will discuss pooling operations, which are also quite common to use in CNNs today. So let's dive right in.
Introduction to convolutional neural networks. Let's first review the structure of a regular multi-layer perceptron that you learned about a few lectures ago. If you remember, multi-layer perceptrons often have this structure that contains an input layer, one or more hidden layers, and then an output layer. More importantly, these layers are always fully connected, which means that every neuron in one layer is connected to every other neuron in the subsequent layer. This gives you a lot of parameters to learn really complex functions, but at the same time, for some problems, this capacity can become too big. So if you only have fully connected layers in a really large network, you often have a significant amount of parameters. And when you don't have massive amounts of training data, then your network can tend to overfit. This is one of the reasons that we have these more structured neural networks called convolutional neural networks, or CNNs. CNNs have this typical structure, which you see here in this slide. So instead of having input vectors, we have these two-dimensional images, or rather three-dimensional tensors, because images, as we all know, have three channels. And these three channels are R, G, and B, red, green, and blue. So this input is then sent to a convolutional layer here, which has these masks that are slided over these input pixels. And this creates an output here in the activation map. So the kernel or the filter mask is connected here to the activation map, which produces an activation at this point when the filter is slided at this particular position. You can have a lot of weights here that is connected to these different neurons. And each of these weights are learned by backpropagation. So there's one weight for every pixel in this mask when it is slided over this particular position. We will talk more about how these are combined exactly in this operation of a convolution. So after the convolution, you can have a nonlinearity such as an ReLU, and sometimes you can also have these pooling layers. So pooling layers do what we called as downsampling to get more manageable representations. And this downsample volume is again input to the next block and so on. So you often have these stacks of blocks of convolution ReLU pooling. And in the end, in order to perform classification, we have these fully connected layers. So this gives us the classification output here. And in this case, we want to classify this input image as a tiger or a lion. Now, representing these layers as blocks, we have an input volume, which can be an image, or it can also be an activation map from a previous layer. So this input first goes into a convolutional layer, followed by a nonlinearity such as an ReLU. You can then have pooling layers depending on the task that you're performing. but you don't always need to have them. So in many networks, you only have them at certain intermediate stages for downsampling. And in the so-called fully convolutional networks, you don't use them at all. So these fully convolutional neural networks are often used for tasks such as semantic segmentation, depth estimation, and so on. And we will learn more about them in the following lectures. CNNs are well suited to learn from structured input data, especially from grid structures such as images. But they're also often very successful in audio processing. In time series, you can have convolutions across time. And in the image domain, you have these 2D filters that you slide over the input image, as we saw in the previous slide. So you can also have 3D convolutions for certain tasks such as learning from videos or in medical applications to learn from multidimensional fMRI images. And these networks are tremendously successful. So they have revolutionized fields such as computer vision, where in most tasks, these networks are currently the state of the art today. So you can even say that for most applications that involve learning from images or even audio data, these networks are quite standard to use. Although I should say that in some applications, RNNs or recurrent neural networks perform a bit better. So we will learn about recurrent neural networks in the next week. So since CNNs are so important, let's take a look at some applications where they are used. So the most fundamental recognition task is image classification, where you train an image on large amounts of labeled data. Here you train the network to classify what object is present in the image. On the left, you see examples from the CIFAR-10 dataset, which consists of object classes such as aeroplanes, automobile, bird, cats, and so on. And on the right, you see some examples from the popular ImageNet dataset, as well as some predictions from AlexNet, which was the first CNN-based approach that won the ImageNet or the ILSVRC challenge. So we will learn more about the architecture of AlexNet in the upcoming lectures. But here you can see some example classifications from AlexNet. This was from 2010. And you can see that most of these predictions are quite accurate. Like the first image, it classifies as a mite. The second image, it even classifies it exactly as a container ship. We can see some slight misclassifications in the bottom here. Here you can see that there is damnation as well as some cherries. But the correct answer is supposed to be cherry, but this is kind of ambiguous here because there's also a damnation, and the network predicts this as damnation. All right, so here we see some more complex computer vision tasks such as object detection and semantic segmentation. On the left, you can see object detection, and on the right, you can see semantic segmentation. And for detection, you train these networks to localize an object in the image by regressing these bounding box coordinates, as well as classifying what type of object is present inside this bounding box. So there's been a significant progress in detection networks, and now these networks also perform really well in very challenging situations, such as heavy occlusions where only parts of the entire object is visible in the image. So on the left, you can see some object detection results using the faster RCNN architecture. And this is on the Pascal VOC 2007 test set. Here, the network localizes objects by regressing the bounding box coordinates, and it also classifies the objects inside them as either a horse here, or a cat or a dog, a bus, and so on. Now we can go to even more complex tasks such as semantic segmentation, which you see here on the right. semantic segmentation is a much richer task. So here we not only localize objects by just regressing bounding boxes, but here what we want to do is we want the network to classify each pixel as belonging to a specific semantic class. So we also want to get this pixel level information here. This is called a fine-grained classification task or a dense prediction problem. So we get a pixel-wise dense prediction, and the network has to identify here also the precise boundaries of these objects, which mean where the classes change to another class type. For example, here these colors indicate that this is a person and this is a horse here. And we want to exactly identify with a lot of accuracy where this change in boundaries takes place. So this is really important in applications such as robotics and autonomous driving, where the self-driving car needs to know which part of the image is the road or the person, or which is the sidewalk, and so on. So there's also a lot of interest in automotive companies in these technologies nowadays, and this is also one of the main driving factors in this field. So we have other more complex tasks. Here we see some example for a task that is called panoptic segmentation. So panoptic segmentation takes this one step further. So we saw semantic segmentation in the previous slide, where we want to do this pixel-wise prediction of pixel-wise classification task. Here, in addition to the pixel-wise classification, we want to combine this with detection. And we also want to identify if one instance of an object is different from another instance, meaning if one instance of a car is different from another car. And we combine this task, which is called instance segmentation, with semantic segmentation to give us a more richer task, which is called panoptic segmentation. And this is some work here from Freiburg from my lab. Okay, so there are various tasks that are dominated by convolutional neural network approaches. Here are some examples from autonomous driving again. So on the left, we see 3D object detection using RGBD data. So here we're not only dealing with images, but we're also using depth data. And you want to regress these 3D bounding box coordinates, not only the 2D bounding boxes as we saw in the previous slides. So then we can also do another dense prediction task that is called depth estimation. Here we want to do some, here we're showing some very recent results of self-supervised depth estimation. You'll also learn about self-supervision in the subsequent lectures. But here what we are doing is estimating depth for each pixel in this image. And on the right, we see a motion prediction task. So this is also some results where we do multitask learning. So in addition to object detection, we also want to predict where these objects are going to move in the future. And in all of these autonomous driving tasks, CNNs are pretty much the standard today. Another really interesting problem beyond just recognition is image captioning. This really surprised people when it came out initially. So here we use a CNN to extract features from images, and these features are then fed into a recurrent neural network that learns to describe what you see in these images in the textual form. So you would train these networks with several examples of images and the correct captions, as you see here below the images as labels, and you will train these networks to predict these captions. So on the left, we see some very good examples without any errors. For example, here you see predictions from different types of networks, such as only CNNs or CNNs with LSTMs and the ground truth. And here, for example, the ground truth says 2 bears touching noses standing on a rock. And our CNN network predicts 2 bears are walking on a rock in the zoo. Or here, if we add an LSTM to it, we get a bear is standing on a rock in a zoo. And as you can see, these predictions are very descriptive about what's going on in this image. So in the next column here, you basically see some older results. So on the right, we see some small errors, basically. So in the first image, it says here that 2 dogs are playing on the grass, where we see that we have 3 dogs. And on the bottom, it says that 2 hockey players are fighting over a puck, but this other person is actually far behind, and only this person is there in the front. So these are very minor errors. And here on the left are more recent results using CNNs on LSTMs. And these results you see, in fact, are from 2018. And actually, this is quite a long ago in the deep learning world. So now these networks have significantly advanced. What really is exciting is that these people have also now developed solutions to the inverse problem. So this means that you can input captions, such as these captions to the input to the network, and the network now learns to generate images as close as possible to these textual descriptions of captions that you input. And this is often done with networks that are called generative adversarial networks, or GANS. And GANS have been really successful in this inverse task. So another example that we have here is skeletal pose estimation. This is not only an important problem in computer vision, but also in robotics as well. So from just 2D images of humans, here we want the network to extract the 3D pose of the human. So this is also what the Kinect camera does, but Kinect actually uses an active infrared sensor in addition to a color camera. And I think most of you might already heard of the Kinect sensor because it comes with the Xbox, and it enables you to control a game by estimating the, let's say, pose of your shoulder, elbows, different joints, and so on. So this is an important example, for example, in imitation learning in robotics, where you want to teach your robot new skills. And here you want to understand where the arms and legs of the human are and what trajectories these are following, to then use these to teach the robot what actions to perform. So CNNs have also been used for weather forecasting. Here we see an example of CNN-based forecasting of thunderstorm on the left and heavy rains on the right. And we see the CNN predictions in blue, and the real observations are shown by these black dots that you see here. Whereas the red lines depict the forecast by expert meteorologists. For the next one here is an application of reinforcement learning. So these are examples from Google DeepMind, where they trained CNNs that extract features that are used to estimate a Q function. So for those of you who are also taking the reinforcement learning lecture, this might be more familiar to you. To estimate the state action values in a reinforcement learning task, they use them to play an Atari, Go, chess, and shogi games. So they trained this on 49 different games in the initial paper, and these games have been able to reach superhuman performances in some cases. So the algorithm only sees the pixels as the input, pixels of the image as input, and receives the scores as feedback. But so it doesn't know what the actual rules of the games are. And here the algorithm had to figure out the policy for which it can have good ways to control the joystick, for example, in order to get the highest score in this game. So there's also a lot of research on training robots with reinforcement learning and imitation learning here in Freiburg. So this is some example research from my lab, where we train a robot to perform various tasks, such as opening a microwave door, or plugging these chargers on the wall sockets, or opening pans, and so on. And here we do this by demonstrating to the robot how the task should be done, and these demonstrations are done by humans. Now, the interesting aspect is that we incorporate human feedback while learning. So here the human can give two types of feedback to the reinforcement learning or the imitation learning algorithm. And this can be a corrective feedback or an evaluative feedback. So here the human can give corrective feedback by manually correcting the trajectories using the keyboard keys or a joystick, or it can also give evaluative feedback, but just saying what the robot is doing is right or wrong. And we show that by using this feedback, we can train a robot to perform tasks from scratch in the real world within about 1 hour, whereas typical reinforcement learning methods takes hundreds of hours. So we also have a lot of research on CNNs here in Freiburg. Here you see work from Professor Thomas Brux's lab. So they did this really cool work on estimating optical flow, where you input two images that are captured consecutively, and you want to estimate the motion of the pixels between the two frames here. So you estimate the direction that the pixels move between these two frames, as well as the magnitude of the movement. And this is very important to estimate velocities of objects in the context of robotics, autonomous driving, and so on. And what you see here is also a fully convolutional neural network. As I mentioned before, that these FCNs or fully convolutional neural networks have no pooling layers. So we do this downsampling of the feature maps that become smaller and smaller using strides. And we will learn about this in the upcoming slides. And after we get to these smaller and smaller downsampling stage, we then upsample these feature maps back to the input resolution using upsampling layers. And we will also learn about upsampling layers in the subsequent slides in the miscellaneous convolutions part. So optical flow is a classical computer vision problem. So before CNNs, this was done using various traditional methods that you might also have learned if you had taken the computer vision lecture here. But these traditional methods were nearly impossible to do this in real time, versus the CNN-based approaches perform faster than real time nowadays. All right, so that brings us to the end of this video, and I have one question for you. So are CNNs only effective for learning from images, or can they also learn directly from other modalities? For example, raw sound waveforms that do not have this natural spatial structure that we see in images. Thank you, and I will see you in the next video.